Hello there. In this lesson, we're going to look at how the current and the voltage at different loads within a circuit compared to the current and voltage at a power supply in that circuit. And once you learn those patterns, there's some neat sort of puzzle type circuit solving that we can do at the end. So of course, by now, hopefully everybody's accustomed to picking out whether a circuit is a series circuit or a parallel circuit. If the loads are in one pathway, like this one on the right, that would be a series circuit. And if there's multiple pathways, like this one on the left, that's going to be a parallel circuit. So let's get started. The first one we're going to do is look at how the current of different loads compares to the current at the power supply in a series circuit. So here we have a power supply with two cells on this battery and goes through the switch. It's got this LED here, and then it's got this motor here, and then back to the power supply. Similarly, down here we have the diagram showing the same thing. We've got the negative and the positive here, and we've got electrons going through this series circuit. Now, current, as you recall, is the rate of electron flow. And the neat thing about a series circuit is that wherever you measure the current, let's say we put our ammeter here, or we put our ammeter here, or our ammeter here, or way over here, it doesn't really matter because the electrons are all sort of stacked along these wires and through the load, all packed next to each other. So the rate of flow of electrons in one spot will be the same at every other spot because there's no other place for these electrons to go. And you can think of them all as being kind of like a traffic jam of cars, and no one electron can move without all of the rest of them moving together. So expressed as an equation, you can say that the total current at the power supply will be the same as the current at any of the loads. Now, in a parallel circuit, things are a little different. Again, you can imagine the electrons coming out from this negative terminal of the battery. And when it gets to this point, there's sort of a splitting that occurs. Some of the electrons will go this way, and some of them will go that way. And that means that the current is going to be less going through any of these loads than back here, where they had come together going in and out of the power supply. So the electrons will come around here, back to this point. These electrons will come around here to the same point. And then they join together to go back to the other side of the power supply. So to represent that mathematically, the current in the first branch, let's call this the first branch, will be added to the current at the second branch. And then when they come together at this point, or before they split at the other point, that's going to equal the total. And if you have more branches, you just continue adding as you go to get the total current for the whole circuit. So a simple way to deduce, if you understand what we've just gone over, would be trying to figure out what the currents are at these other points along this circuit at I2 and I3, and this here would be the I total. So since this is a series circuit, you might recall that the current is all the same throughout the circuit. So if you know that it's 0.25 amps through this bulb, well then it's got to be 0.25 amps at this bulb and 0.25 amps here. And way back at the power supply, also 0.02, oh, too many zeros, 0.25 amps there as well. Now for a parallel circuit, they got to add up. So if the total current is 1 amp, and you got electrons coming out here and then going this way and then this way and then this way. If you got a quarter of an amp going here and a quarter of an amp going here, you can just subtract from the total to figure out the remaining value. So 1 amp minus 2 quarters means that this is going to be 0.5 amps going through this, this last branch. Okay, so the second pattern we're going to look at are those that deal with potential difference or voltage. We'll start with series. If you recall, the potential difference is the difference in energy between 2 points in a circuit. And that difference, of course, divided by the charge. And because there's only one pathway in a series circuit, the energy that is going to be given off by this bundle of electrons traveling through this circuit has to be shared between the loads that are going to use it. So the total difference in energy at this power supply, or the total, as it's often shown, will be the sum of the potential difference at each of the loads that are in that pathway. So if this is V1 and this is V2, then the total voltage is going to equal the sum of the voltages in the pathway. And if there are more loads, you would just add more to this series, and you can just add them up. Alrighty, so to finish this off, the potential difference in parallel follows the same pattern as the current in series, where the total voltage, or the voltage at the power supply, is going to be the same as the voltage of any one of the pathways. The reason for that is, again, if you are a bunch of electrons and the voltage is the potential difference of the energy from the start to the finish, if electrons go through this pathway, they're going to have to give up all of that energy in order to be at the bottom of the waterfall by the time it gets to the other side. A different batch of electrons might take this second path, but then again, it has to give up all that same amount of energy in order to be at the bottom of the waterfall on the other side. So that means that the total voltage at the power supply is going to be equivalent to the voltage at any of the pathways. And if you have more pathways, they will also have the same voltage. So if you want to solve for any missing values in a circuit, if it's a series circuit, remember that the total voltage is the sum of the voltages of the loads in a given pathway. So you can add those up. So if the sum is 8 and we've got a 2 and a 2, that means this one has to be 4 volts. And then the voltage in a parallel circuit is going to be equivalent for each pathway. And so if you know one, then you know all of them. So if this is 6 volts, that means this here is going to be 6 volts, and this is going to be 6 volts, and the power supply will be 6 volts. So as long as you can sort of keep that straight, there's usually lots of values that you can quickly assume using these equivalences or sums from the relationships that we've learned. All right, so now it's where the fun begins, because for each of the loads or the power supply, you can use the relationship between the potential difference and the current in order to get either the resistance, which is when you divide the potential difference by current, or the power, which is when you multiply them. And so you can use that. Let's say in this example, we have a 6-volt power supply and 2 ohm resistance. If I want to figure out the current, it's going to be V over R, which is going to be the 6 volts divided by the 2 ohms. And so that means we have 3 amps. So it's going to be 3 amps. And then if I want to figure out the power for that, well, power is the product of those two. So power is going to be the 6 volts times the 3 amps, and that'll give us 18 watts. Likewise, over here, we've got the current and we've got the power. So if we want the voltage, it's going to be the power divided by the current. So we've got 72 watts, and we're going to divide that by 6 amps, and that'll be 12 volts. And then, so that goes here, 12 volts. And then if we want the resistance, resistance is V over I. So we take the 12 volts and divide it by the 6 amps, and that's a 2 ohm resistance. So 2 ohms. And this was 18 watts. Great, so for any value, as long as you have some of the pieces, you can work out the others using these handy relationships. Alrighty, so now we're going to do the little circuit puzzles, which I really enjoy. This one is a series circuit, so we're going to include the relationships for series, and you can see we're also given some resistance values, and we're going to use those resistance relationships for that. So I always like to start with the easiest part, which are the things that are all the same. And in this case, we do have a current here, so that means we can fill in all the other currents because in a series circuit, they're all the same. Great, and then we'll look for any other relationships we can use. We can see we have a total voltage of 15 volts, 5 volts are used up with this load, 4 volts with this load, and so to make that total of 15, this one has to be 6 volts in order for that to add up. Finally, for the resistances, we can use this handy relationship here, and we can just divide. So 5 divided by quarter, that's like multiplying by 4. That's going to make this 20 ohms. 6 divided by quarter is going to be 24 ohms. 4 divided by quarter is going to be 16 ohms. And 15 divided by quarter is the sum, which is 60 ohms. And we'll learn more about that relationship for resistance in the next lesson. Finally, we're going to do this little puzzle here, which has a parallel circuit. So we're going to use the parallel relationships. Here they are. The current adds up for each of the branches, and the voltages will be the same for all the branches. And this time we're given power to help complete things, and so the relationship between current and voltage and power is given there. So again, I would look for a voltage, or to calculate a voltage first, so that I would be able to fill in all these because they're all equivalent. And I see I've got one, yay! So that means 5 volts for all of these. Great. Secondly, I only have one of my currents here, so I can't really solve for the currents because I have 2 that are missing here. However, with this guy, we can see that we have the voltage and the power, which means we should be able to work out what this current is. So let's do that. We'll use this relationship here. We want to know the current, so I equals P divided by V. The power for that one was 2.5 watts, and we're going to divide it by the 5 volts. And 2.5 divided by 5 is going to be 0.5 amps. So 0.5 goes in here. So we've got 1 amp, and we've got 0.5 amps, and we got to add this guy to get to 1.75 amps. So we're at 1.5, and we got to get to 0.75. So that means this one here is 0.25, because all 3 of these, 1, 2, 3, have to add up. Have to add up to the overall current, right? Current 1, current 2, current 3. We had a 1, we had a 0.5, and this is one we didn't know, but we knew the sum was 1.75, and so you subtract those from the one you started with, and that's how we knew that this must be 0.25 amps. Great. So now that we're done all that, we've got 2 out of 3 for all that remain, and that means we can just use this relationship for power to get what remains. So 5 times 1.75, I don't know that off the top of my head, I'm going to have to get a calculator here. So that multiplies to 8.75 watts. And then this guy, 5 times a quarter, 5 times 0.25 is 1.25 watts here. And we got this one already. And finally, we got 5 times 1 is 5 watts. And that means that we've solved the puzzle. We've got all of the readings for all of the loads and the power supply. All right, hope that was helpful.